Myself, Madhuri Modak, Assistant Professor in Mathematics, Department of Computer Science, Abhidanandar Senior College. Discrete mathematics is very important for students of computer science. Now here we start with unit number 3, Techniques of Counting of Discrete Mathematics. Now the first point is basic counting principles. Now first see what is the meaning of cardinality of S, where S is any set. Now let S be a set. If there are exactly n distinct elements in S where n is a non-negative integer, we say that S is a finite set and n is the cardinality of S. We denote the cardinality of S by this symbol. So if you consider any set S which contains exactly n distinct elements, means no two elements in S are same, all are different, where n is any non-negative integer, means n is either 0 or positive. Then in that case we say that S is a finite set and n is the cardinality of set S denoted by this symbol. Now, if S equal to 5 means empty set, then S contains nothing. So, no element in S. So, cardinality of S is equal to 0. Now, see some examples. Let A be a finite set of odd positive integers less than 15. See what are the members of A. So, odd positive integers are the numbers which are not divisible by 2. So it contains 1, 3, 5, 7, 9, 11, 13. Now count the number of elements in A. They are 7 in number. So cardinality of A is equal to 7. Here we are not taken 15 because we are considering in A integers, odd integers less than 15. So 15 will not be there in A. Now second example, let's S be the set of letters in the English alphabet. It means S contains the elements A, B, C, D up to Z, which are 26 in number. Hence cardinality of S is equal to 26. Now see the definition of power set. The power set of set S is the set of all subsets of the set S and is denoted by P of S. So if you consider any set, it has many subsets. So if we are considering the collection of all subsets of S, then it is again a set and that is known as power set of S denoted by P of S. Now see, what is the power set of the set S equal to APC? Now S contains three elements A, B, C. So the possible subsets of S will contain 0, 1, 2 or 3 elements. Not more than that definitely. So what is P of S? It is A such that A is subset of S. So we start with 0 element subset of S, that is empty set, because empty set is subset of every set. Then form the subsets of S containing one element. So it is singleton A, singleton B, singleton C. These are one element subsets of S. Now form the subsets of S containing two elements. So one is AB, then BC and AC. And finally, by taking all three elements of S, that is A, B, C. So these are all possible subsets of S. So this is nothing but power set of S. Now, what is the power set of empty set? Now see, the empty set phi has exactly one subset, namely phi itself, because every set is subset of itself. So even though empty set does not contain any element, its power set contains one element, namely phi itself. Now, there is one important thing. If S contains n number of elements, it means cardinality of S is equal to n. Then cardinality of P of S means number of elements in P of S is equal to 2 raised to n. Now, see in first example, S contains 3 elements A, B, C. So, cardinality of P of S is 2 raised to 3, that is 8. See the elements 1, 2, 3, 4, 5, 6, 7 and 8. So if S contains 3 elements, then cardinality of P of S is 2 cube. Similarly, if S contains 5 elements, then cardinality of P of S will be 2 raised to 5, that is 32. Now, the next important rules are product rule and sum rule. Now, product rule is also known as multiplication principle. See the principle. Suppose that a procedure can be broken down into a sequence of two tasks. If there are n1 ways to do the first task, and for each of these ways of doing the first task, there are n2 ways to do the second task. Then there are n1 into ways, n1 into n2 ways to do the procedure. See, the entire procedure or method, it is divided into sequence of two tasks. Now to do the first task, there are n1 ways, and for each of the ways of doing that first task, again there are n2 ways to do the second task. Then there are n1 into n2 ways to do the procedure. Now see the remark. The product rule can be phrased in terms of sets as follows. If there are n1 different objects in the first set, n2 different objects in the second set, and if the two sets are disjoint, then the number of ways to select one object each from both the sets is n1 into n2. See, what is the another way of stating the product rule? Now there are two sets. First set contains n1 different objects. Second set contains n2 different objects. And the two sets are disjoint. Means nothing is common in their intersection. Now we have to select one element from first set and one element from second set at a time. And in how many ways we can do it? It is n1 multiplied by n2. Now see sum rule or addition principle. If a task can be done either in one of n1 ways or in one of n2 ways, where none of the sets of n1 ways is the same as any of the sets of n2 ways, then there are n1 plus n2 ways to do the task. See, now the task can be done either in one of n1 ways or in one of n2 ways. So whenever there is either or, at the same time none of the sets of n1 ways is same as any of the set of n2 ways, then to do that task total number of ways are n1 plus n2. Now another way of saying the sum rule or addition principle is if there are n1 different objects in the first set, n2 different objects in the second set, and if the two sets are disjoint, then the number of ways to select an object from one of the sets, means either from first or from second, is n1 plus n2. Now see, alternate way of stating sum rule is suppose there are two sets, first set containing n1 different objects and second set containing n2 different objects, and the two sets are disjoint. Now if we want to select one element either from first set or from second set, then in how many ways we can do it? It is n1 plus n2. Now see what is the difference between product and sum rule. Now here same sets were given containing n1 and n2 objects respectively. But here from each set we are selecting one element. So from n1 elements we are selecting one, and from n2 elements we are selecting one element. And here overall we are selecting only one element. So that is the difference. Now, these are some examples based on product and sum rule. Now, see the first example. In a class, there are 30 boys and 25 girls. The teacher wants to select one boy and one girl to represent the class. In how many ways can the teacher make this selection? See, there are 30 boys and 25 girls. Now the teacher select one boy and one girl to represent the class. So out of 30 boys, teacher will select one boy, and out of 25 girls, teacher will select one girl. It means at a time we are selecting one element from both the sets, from boys set as well as from girls set. This is not either or, but this is and. So we have to use product rule or multiplication principle. So there are 30 boys, one boy we have to select. So there are 30 ways to select one boy, and 25 girls are there, we have to select one girl, so we can do it in 25 ways. So by product rule it is 30 into 25, that is 750. Then in second example, see what is the difference. In a class there are 30 boys and 25 girls. So same thing is given. The teacher wants to select one student to represent the class. In how many ways can the teacher make the selection? Now instead of selecting one boy and one girl means total two students, here we have to select only one student. It means it may be a boy, it may be a girl. So either from 30 boys we have to select one boy, or from 25 girls we have to select one girl. So it is similar to sum rule. If there are two sets containing n1 and 2 different objects and we have to select one object either from first set or second set, then it can be done in n1 plus n2 ways. So as there is either or, either boy or girl, the required answer is by sum rule 30 plus 25, that is 55. Now third example, a store carries 8 styles of pants. For each style there are 10 different possible waist sizes, 6 pant lengths and 4 color choices. How many different types of pants could the store have? Now see, for each style there are 10 different waist sizes, 6 pant lengths and 4 color choices. So here again we have to use multiplication principle or product rule. So answer is 8 into 10 into 6 into 4, that is 1920. Now, it is important to recognize which rule should be applied to solve that example. So, whenever two things we are doing at a time, it means there is and, then we have to use product rule or multiplication principle. But if there is either or, then we use addition principle. Now, see fourth example. An office building contains 27 floors and has 37 offices on each floor. How many offices are in building? See, on first floor there are 37 offices. On second floor there are 37 offices. Means for each floor there are 37 offices and 27 such floors are there. So actually it is 37 plus 37 plus 37. How many times? 27 times. So it is nothing but the product rule. So by product rule, total number of offices in the building, if there are 27 floors and 37 offices, is equal to 27 into 37, that is triple nine. Now next, there are 18 mathematics majors and 325 computer science majors at a college. It means there are 18 students who have taken mathematics as a major subject and 325 have taken computer science as major subject. Now first, how many ways are there to pick two representatives so that one is a mathematics major and the other is a computer science major? Second, how many ways are there to pick one representative who is either a mathematics major or a computer science major? Now, this problem you can compare with the problem of selecting one boy, one girl, or only one student representative. Now, in first case, we have to select one mathematics major and one computer science major. So here we will use product rule. So by product rule, required number of ways is 18 multiplied by 325, that is 5850. And in second, one representative, so it will be either mathematics major or computer science major. So by sum rule or addition principle, it is 18 plus 325, that is 343. Now next, how many different three letter initials are there that begin with an A? Now see, we have to form different three letter initials, but the condition is that it should begin with A. So if it should begin with A, on the first position we have to keep A only. Now for second and third position we can use any letter from A to Z. So for second there are 26 ways or choices. Similarly for third also there are 26 choices. But as we have to form a three letter initial, we must fill second and third place at a time. So by product rule, as we are doing second and third place at a time, by product rule or multiplication principle, required answer is 1 into 26 into 26, which is 676, because to fill first place there is only one way, that is filling by A, and for second, third there are 26 choices, and we can repeat the letter which we have used on second place for third place, because it is not given that repetition is not allowed. Now see example 7. How many three-digit numbers can be formed by using 1, 2, 3, 4, 5 without repetition of digits? So forming a three-digit number means we have to fill unit place, tens place and hundred place. Now here the condition is that repetition of digits is not allowed. Now first see, we can use 1, 2, 3, 4, 5. Now if we are starting with the hundred place, now hundred place means first place, it can be filled by any of the digit 1, 2, 3, 4, 5. So there are 5 ways to fill that place. Now after using one of the digit at hundred place, we cannot use same digit at tens place because repetition is not allowed. So from remaining 4 digits, we have to fill the tens place. So for tens place there are four choices. Now after using two digits for hundred and tens place, we cannot use both the digits for units place. So remaining three digits we can use for units place. As we have to form a three digit number, all three places we have to fill at a time. So by product rule or multiplication principle, required answer is 5 into 4 into 3, that is 60. Now next, how many functions are there from a set with m elements to a set with n elements? So there is one set, say A, which contains m elements, and another set, say B, which contains n elements. Now we have to form functions from set containing m elements to set containing n elements. So each element of domain can be mapped to any of the n elements of the codomain. It means first element we can map to any of that n elements of codomain set. Then after mapping that element again, second element can be mapped to any of that n elements, because first, second, even all elements can be mapped to single element. That is allowed in case of function. So second element can be mapped to any of that n elements. Likewise, third element can be mapped to any of that n elements. And in this way, mth element can be mapped to any of that n elements of codomain. So by product rule, there are n into n into n m times, that is n raised to m functions from a set with m elements to one with n elements. Now, next example. If cardinality of A is 5 and cardinality of B is 7, how many functions are there from set A to set B? Second, how many 1 functions are there from set A to set B? Now, first is directly using example 8 we can do. Now, each element of A can be mapped to any of the 7 elements of B. Hence, number of functions from set A to set B is equal to 7 into 7 into 7, 5 times, which is 7 raised to 5. So instead of m and n, here the particular values of cardinalities of two sets are given. Now, second is quite different. How many 1 functions are there from set A to set B? Now, 1 is a type of function in which distinct elements have distinct images. Means no two different elements from domain set can be mapped to single element from codomain. It means if x and y are different elements of domain set, then their images must be different elements. So that precaution we have to take. So in 1 function, two different elements of A should be mapped to two different elements of B. So for the mapping of first element, we have all 7 choices. But what will happen after mapping first element to any of that 7 elements, second element we cannot map to previous element. So excluding the image of this element, we have 6 choices for mapping second element of A. Similarly, we have 5 choices for the image of third element. 4 choices for fourth element and 3 choices for the fifth element. Hence, by product rule, number of 1 functions is 7 into 6 into 5 into 4 into 3, which is equal to 2520.